Okay, so in this video we're going to explore loop invariants. We're going to work on one more problem that involves loop invariants, and more specifically for this problem we're going to look at this idea of the power function. And the way the power function is defined is, let's say if I have two inputs provided, let's say my two inputs are x and a. X and A are two inputs that are being fed into a certain function. So let's say mathematically this function over here is some function f. I have some function f over here that takes in these two parameters, and you are asked to implement this method f that gives you back in this case what is x raised to the power a, meaning what you're going to give you back is some value which is x to the power of a. So write me a function f, or more specifically the power function that takes in two parameters and gives you back x to the power a here. And again, just to be a little bit consistent, just to be consistent with this, I'm going to have a precondition. I'm not going to enforce this condition in my code here, because I would just like to concentrate a little bit more specifically on the loop invariant aspect of it. But let's just assume that a is something that will be greater than 0. Okay, so you're going to have a as something being greater than 0. So given that precondition over here, let's just formulate our code in Python. So so in Python, let's do this. Let's just formulate our solution. So let's say def. I have a method power, and power is something that takes in two parameters. It takes in x and takes in a. And what I need to know at this point is I just need to start thinking a little bit more. What is my loop invariant going to be? How am I going to even phrase my loop invariant here? So in order to phrase my loop invariant, what I'm going to say at this point is let's just create two local variables. Let's just create two local variables. So let's just create a local variable y and b. So I'm going to say y local variable is something that's equal to x, and then I've got my second local variable b, and let's have b equals to a. Given my two local variables y and b, my loop invariant, the way I'm going to define my loop invariant here. So let's say, let me just use a different color here. So let's just use maybe slightly a white color here. So let's say my loop invariant at this point. The way I'm going to define my loop invariant for the power function is that in this case x raised to a, x to the power of a is equal to y raised to the power of b times some result. Okay, so I have x to the power of a equals to y raised to the power of b times some result there. Okay, let's just hold on to that thought just for time being, that if this is what my loop invariant is, what I need to do is that if I'm going to have a loop introduced somewhere in my code here, if I'm going to have a loop introduced somewhere in my code over here, and then I'm going to have a body of my loop. So at some point, let's say this is the body of the loop over here, and eventually I'm going to return back a result. I'm going to return back some results. I'm going to have, just as a very last line of my function, return result. So this result over here is going to contain that value which is going to be whatever is x to the power of a. Whatever is x to the power of a is going to get collected in this variable result. So with loop invariants, the few things that we have learned over here, actually in the earlier videos, is that there are specific points in my code that this loop invariant over here must hold. What are the specific points that this loop invariant must always hold, meaning it should always be true? One of the points is right here, just before the start of the while loop. So let's call this point 1. I have another point 2, which is just before the start of the body of my loop. The third point over here is just after the body of my loop here. Let's call it point 3. And the other fourth point could be, in this case, is the just after the termination of my loop. Just after the loop terminates, I have this fourth point over here that must also be a certain specific point that the loop invariant must hold. It shouldn't be violated at any of these 4 points here. Okay, so what is it I should do, or let's think about this. If my if this specific point at 1 is where a loop invariant must hold, what should I declare result as? What should result be, so that at 1, just before the start of the while loop, my loop invariant actually holds? So I can just say at this point, that let's just say result is something that equals to 1. So by having result equals to 1, at point 1, just after result equals to 1 and just before the start of the loop, if I just plug in some value here, let's just plug in some value for x, let's plug in some value for a. So let's say if x in this case is 2, or let's say x as 3 and a as 2, I have 3 raised to 2 equals to 3 raised to 2, because y is equals to x and b equals to a, times the result. My result is 1. So 3 square equals to 3 square times 1 holds, meaning my loop invariant is actually true at point 1. Okay, now let's just think about a loop here. What is it that I need to do over here so that my loop comes to some kind of a convergence? It at least comes to a termination. What is it that I must do in my loop here? So at least one thing is that I can look at this b here, and I can start thinking about, let's take this b, and let's just say as long as this b is greater than 0, okay, if this condition holds, do something in this body of the loop, but the very last statement is going to be b minus minus. Okay, now I'm just exploring one specific idea here, where I'm decreasing b linearly by just doing a subtraction. But sure, you could also, there's other various algorithm that would actually look at b being divided by 2. So what I encourage you to do is, after watching this video, redo this problem by exploring what if I were to do if b were to get decreased by half, meaning then you need to look at slightly at two specific conditions, if b is even or b is odd. But I'm not going to explore that idea, at least in this video here. So I'm going to take where b decreases by 1 here. So if b, as long as b is greater than 0, do something in this yellow box, but the very last statement is going to be minus minus, meaning that this loop does come to a termination. At some point, b will be equal to 0, just at this point for when the loop breaks. When this loop breaks over here, b is going to be equal to 0, and when b is equal to 0, the loop is going to break here. Okay, so what is it that my result is going to be at point 2? What is it my b is going to be at point 2? So let's just make something up here. So let's just use some subscript notations. So let's say that at point 2, my loop invariant is x raised to the power a. Remember, x and a are constants. X and a is never ever going to change in my code here. So x to the power a equals to, at point 2, what I'm going to have is, let's say whatever is y at that point, y subscript 2 raised to b subscript 2 times whatever is result at that point. Let's call that result 2. Okay, what is it that my loop invariant is going to be at this point 3? At point 3, well, I'm still going to have x to the power a. Okay, because the loop invariant says that whatever is at point 3, I still should have whatever is y to the power b times the result still should be equal to x to the power a. So x to the power a is going to be equal to y subscript 3 b 3 times result 3. Now if my loop invariant holds at point 2 and holds at point 3, meaning it's actually true at point 2 and it's true at point 3, so meaning if this is my loop invariant at point 2, this is at point 3, so I know that I can just equate the two together, and if I just equate the two together, I can just rewrite this. Let's just rewrite the orange part as y2 b2 times result 2 equals to equals to y3 b3 times result 3. Okay, can I do something with b2 and b3? Can b3 be written in terms of b2? Well, sure, it can be written because if this is whatever at this point is b2, there's some value b2 over here. Okay, this b at 3, whatever is this b3 at 3 is just equal to whatever was b2 earlier, b2 minus 1, right? This is something I'm remembering straight here, b minus minus. So b minus minus meaning b has already decremented by 1. So at this point 3, whatever is this b3 is going to be equal to b2 minus 1. So I can rewrite this slightly differently now. So I'm just going to say y2 b2 times result 2 equals to y3, and I'm going to say b2, let's do this, b2 minus 1, that's right, and times result 3. Okay, now if y is something that isn't going to change, if I'm not going to change y, because what the parameters that I have right now is my y parameter, and I've got my result here. I'm going to keep my y constant. Y is something that isn't going to change in my code. If y is something that isn't going to change in my code, and the only thing that's going to change is the result, because the result is the only remaining parameter that needs to change in order to ensure that this actually holds, this actually remains consistent. So I can just do this as I can just rewrite this as something where y2, let's just use orange here that I was using earlier. So what I have now is y2 b2 times result 2 equals to I'm just going to have y3 and y2 are going to be exactly the same. Those are some of the variables that isn't going to change in my code here. So I've got y2 and here I've got b2 times y2. I'm just going to rewrite this as y2 to the power b2 times y2 to the power minus 1 times result 3. Okay, so what is result 3 equal to then? So result 3, if I look at result 3 here, result 3 is nothing but equal to, if I take this y2 to the power minus 1 on the other side, what I have now is result 2. Again, this is in orange here, so what I have now is result 2 times y2, I'm getting this on the left hand side over here, equals to whatever is this result 3. Okay, so result 3, meaning whatever is this result that's going to be at this point 3, is equal to result 2 times y2. Result 2 times y2, whatever result 2 is going to be something valid at this region over here. Y2 is also valid at that region over there. So I can say result 3, I can say this result 3 over here. So this is going to be result is something that's going to be equal to result times y. Okay, so I've got result equals to result times y, and at this point, what I have now is the complete power function completely implemented. This is the power function over here. And what we're going to do in the next video is we're going to look at this power function, and we're just going to again just to look at these various points in my code 1, 2, and 3, and 4 to ensure that the loop invariant actually holds at these points.